They had been told that American rocket science was primitive, cobbled together from captured German blueprints, and staffed by technicians who could barely comprehend the elegant mathematics that had propelled the V-2 into the stratosphere above London. But when Wernher von Braun and his team of nearly 120 German scientists stepped off the military transport at Fort Bliss, Texas, in September 1945, carrying their leather cases and their assumptions about technological supremacy, they were about to encounter something that would shatter every certainty they possessed about the future of rocketry. It was not a weapon or a blueprint that would break their understanding of what was possible. It was a fuel. The desert heat struck them first, a wall of dry air so different from the damp cold of Peenemünde that it felt like stepping into an oven. Dust clung to their wool suits, those same dark suits they had worn in the laboratories of the Third Reich, now rumpled and stained from weeks of interrogation and travel. They had been the elite, the brilliant minds who had taken humanity to the edge of space itself, and now they stood on American soil as something between prisoners and guests, their status uncertain, their future dependent entirely on what they could offer their new hosts. Von Braun's eyes scanned the horizon, taking in the flat expanse of scrubland and the crude buildings of the military base. This was not what dominance looked like. This was not what the future was supposed to resemble. But within days, they were led into a laboratory complex that smelled of fresh concrete and machine oil, where American engineers in shirt sleeves were working with a substance the Germans had never successfully stabilized. The fuel sat in steel drums, clear and slightly viscous, its chemical designation marked on the side in stenciled letters. Hydrazine derivatives. Hypergolic propellants. The Germans knew these compounds from their own research, theoretical exercises that had always ended in failure or disaster. They had tried and abandoned such fuels years ago, dismissing them as too volatile, too dangerous, too unpredictable to ever function in a reliable rocket engine. Yet, here were the Americans, handling these compounds with casual confidence, mixing them in quantities that would have sent any German engineer running for cover. Konrad Dannenberg stood at the edge of one testing area, watching an American technician pour one chemical into a chamber already containing another. The reaction was instantaneous. Flame erupted from the nozzle with a roar that shook the corrugated metal walls, clean and controlled, burning at temperatures that made the air itself shimmer. No ignition system, no spark plugs or electrical firing mechanism. The fuels simply touched each other and combusted, hypergolic contact creating thrust in microseconds. Dannenberg's mind could not reconcile what he was seeing with what he had been taught. The German program had spent years perfecting ethanol and liquid oxygen combinations, wrestling with the problems of ignition reliability, developing elaborate systems to ensure the rocket engines would fire when commanded. And here were the Americans, bypassing the entire problem with chemistry the Germans had deemed impossible to master. They gathered that evening in the barracks assigned to them, sparse rooms with metal cots and thin mattresses, and spoke in low German voices about what they had witnessed. There was confusion in their tones, and something else beneath it that none of them wanted to name. The Americans had not captured this technology. They had not stolen it from German laboratories or extracted it through interrogation. They had developed it themselves, independently, through their own research programs that had apparently been running parallel to Peenemünde all along. The implications sat heavy in the room like smoke. If the Americans had achieved this, what else had they accomplished in secret? What else had German intelligence simply missed or dismissed? Arthur Rudolph had spent the war years as the production director for the V-2 program, overseeing the manufacturing processes that turned theoretical rockets into actual weapons. He understood propellants and their practical limitations better than almost anyone in the room. The hydrazine compounds the Americans were using would revolutionize everything. They eliminated ignition failure, one of the primary causes of rocket malfunctions. They could be stored separately and mixed only at the moment of use, vastly improving safety. They burned hotter and more efficiently than ethanol combinations, producing more thrust per kilogram of fuel. These were not marginal improvements. This was a fundamental leap forward in rocket technology, achieved by engineers the Germans had believed were years behind them. Sleep came slowly that first night in Texas. The desert cold seeped through the thin walls, and many of the scientists lay awake staring at the dark ceiling, their minds replaying what they had seen. They had been the innovators, the ones who had pioneered liquid-fueled rockets, who had sent missiles higher and faster than anyone before them. The V-2 had been the most sophisticated weapon of the war, a technological marvel that represented the peak of rocket science. But that peak, they were beginning to understand, had been visible only because they had not looked carefully at what others were climbing beside them. The Americans had been quieter about their progress, less interested in propaganda victories and more focused on solving the fundamental problems that would determine who actually controlled the future of spaceflight. The following weeks brought a steady accumulation of small revelations, each one chipping away at the edifice of assumed superiority the German scientists had carried with them across the Atlantic. The American rocket facilities, though less grandiose than Peenemünde, were equipped with instrumentation the Germans had never possessed. Telemetry systems that could track multiple parameters in flight, high-speed cameras that captured combustion processes in extraordinary detail, testing chambers that could simulate altitude conditions with precision. The Americans had been methodical, building infrastructure for systematic research, while the Germans had been rushing to produce weapons under wartime pressure. In the propellant laboratories, the German chemists began to understand the full scope of what the Americans had achieved. The hydrazine derivatives they were using were not single compounds but carefully formulated mixtures, blends of chemicals whose proportions had been optimized through thousands of test firings. There were fuel combinations designated by numbers and letters, each tailored for specific applications. Some burned cooler for longer duration, others provided explosive thrust for launch sequences. The Americans had created an entire library of propellant options, a toolkit that gave their rocket designers flexibility the German program had never enjoyed. Walter Riedel, who had been the chief designer at Peenemünde, spent hours in these laboratories, asking questions through translators, taking notes in his meticulous handwriting. The Americans were forthcoming with information, almost generous in sharing their research. This itself was strange, a kind of openness that would have been unthinkable in the hierarchical secrecy of the German program. American engineers would explain their processes, show their failed experiments alongside their successes, discuss problems they had not yet solved. There was a different culture at work here, one that valued practical results over theoretical purity, that rewarded innovation regardless of its source. One afternoon, an American engineer named Thomas demonstrated the safety protocols for handling the hypergolic fuels. He was young, perhaps 30, with an easy manner that seemed at odds with the dangerous chemicals he was manipulating. He explained that the separate storage of oxidizer and fuel meant that accidents were less catastrophic than with the German approach. A leak in one tank would not ignite unless it contacted the other compound. The engines themselves were simpler, with fewer moving parts, because they did not need complex ignition systems. Thomas spoke about these advantages with no trace of arrogance, simply laying out the technical facts as though they were discussing any ordinary engineering problem. But Riedel heard something else beneath the technical details. He heard the absence of the desperation that had driven the German rocket program. These American engineers had not been racing against invading armies or working with slave labor under the pressure of imminent defeat. They had been methodically solving problems, building knowledge step by step, creating systems designed not for immediate deployment but for long-term development. The difference in circumstances had produced a difference in outcomes. The Americans had been able to take risks the Germans could not afford, to pursue solutions that might take years to perfect, because they had possessed something the German program never had: time. The desert outside Fort Bliss stretched away in all directions, empty and vast. And sometimes in the evenings the German scientists would walk the perimeter of the base, feeling the temperature drop as the sun disappeared behind distant mountains. They spoke less now about their own achievements, less about the V-2 and its triumphs. Instead, they talked about what they were learning, what they were beginning to understand about the American approach to rocketry. Ernst Stuhlinger, a physicist who specialized in electrical propulsion concepts, remarked one evening that the Americans seemed to think about spaceflight differently than the Germans had. Where the German program had focused on missiles and weapons, immediate military applications, the Americans were already planning for satellites and orbital missions, for rockets that would carry scientific instruments rather than warheads. This difference in vision extended to the fuels themselves. The hypergolic propellants the Americans had developed were ideal for spacecraft engines, for systems that needed to fire reliably after sitting dormant for months in the vacuum of space. They could be restarted multiple times, a capability essential for orbital maneuvering that the German ethanol engines could not match. The Americans had been thinking ahead, past the immediate post-war period, toward a future where rockets would be tools of exploration rather than destruction, and they had developed the technology to match that vision. Helmut Gretrup, who had worked on guidance systems at Peenemünde, found himself spending time with American control engineers who were integrating the new propellants with electronic firing sequences. The precision possible with hypergolic ignition meant that guidance systems could control thrust with accuracy the German systems had never achieved. Engines could be throttled, shut down, and restarted, pulsed for fine attitude adjustments. The fuel technology was not just about power, it was about control, about the ability to command a rocket's behavior with exactness. This was what spaceflight would require, this level of precision, and the Americans had understood it years before the Germans had even begun to consider the problem. There were moments of quiet shame in those early months in Texas. Not shame about the war, though that was certainly present for some of them, but shame about the intellectual arrogance they had carried. They had believed themselves to be the undisputed masters of rocket science, had treated the American efforts as amateurish attempts to copy superior German work. But the hypergolic fuels were not copies. They were innovations, original solutions to fundamental problems, developed through research that had proceeded along entirely different lines than the German approach. The Americans had not been trying to catch up to Peenemünde. They had been pursuing their own path, and that path had led to capabilities the Germans did not possess. Von Braun understood the implications faster than most. He was a pragmatist beneath his visionary rhetoric, a man who could assess political and technical realities with cold clarity. In meetings with American military officials, he began to position the German team not as the experts who would teach the Americans how to build rockets, but as colleagues who could contribute to a shared effort. He emphasized what the German team could offer in areas where they still had advantages: guidance systems, structural design, manufacturing processes. But he no longer spoke as though the Germans held all the crucial knowledge. The fuel technology had taught him humility, or at least its tactical simulation. The testing program accelerated through the fall and winter. The Germans participated in launches using American propellants, watching rockets rise from the desert floor on columns of hypergolic flame. The reliability was extraordinary. Mission after mission succeeded, engines firing with clockwork precision, stages separating cleanly, payloads reaching their intended altitudes. The failure rate was a fraction of what the German program had experienced, and each successful flight was another demonstration of the value of the American fuel technology. In January 1946, the first captured V-2 was launched at White Sands, modified with American instrumentation and using the original German ethanol-oxygen propellant. The German scientists watched with mixed feelings as their creation lifted off in American territory, carrying American instruments. It performed adequately, as it had been designed to do, but everyone present could see the limitations that had once seemed like acceptable compromises: the ignition delay, the combustion instability, the relatively low efficiency. These flaws stood out now in contrast to what the American fuels could achieve. Over the following months, discussions began about hybrid designs, rockets that would use German structural and aerodynamic knowledge combined with American propellant technology. The Germans contributed their understanding of fin design, body construction, and payload integration. The Americans provided the engines, fed by fuels that ignited on contact, that could be stored and handled with relative safety, that burned with the efficiency needed for truly ambitious missions. The collaboration was genuine, neither side completely dominant, both bringing essential knowledge to the shared project. But the power dynamic was clear. The Germans were working in American facilities, under American authority, toward American objectives. The fuel technology had established that the relationship would not be one of captured masters teaching eager students. It would be a partnership, but not an equal one. The Americans held the innovations that mattered most for the future. The Germans held historical achievements that commanded respect but not deference. By spring, many of the German scientists had moved their families to Texas, children enrolled in American schools, wives learning English, and navigating American grocery stores. Life in the desert became routine, the strangeness of their circumstances fading into daily patterns of work and domestic life. But the memory of that first encounter with hypergolic fuels remained, a watershed moment that had reoriented their understanding of their place in the world of rocket science. Kurt Debus, who would later direct launch operations for Apollo, wrote to a colleague still in Germany describing the American propellants and the philosophy behind them. He tried to explain how the Americans approached problems differently, how they valued empirical testing over theoretical elegance, how they were willing to pursue solutions that seemed crude or inelegant if those solutions worked reliably. The letter captured something of his own transformation, the way his thinking had shifted from the certainties he had brought to Texas to a more nuanced understanding of how innovation actually occurred. The fuel itself became a symbol of something larger. It represented a different way of thinking about technology, a different set of priorities and values. The Germans had pursued perfection within defined parameters, creating systems of great sophistication but limited flexibility. The Americans had pursued practical solutions that could be adapted and improved, creating systems that were perhaps less elegant but more robust. Neither approach was simply superior to the other, but in the specific context of rocket development in the immediate post-war period, the American approach had produced more useful results. Arthur Rudolph spent time analyzing the manufacturing implications of the American fuels. The production processes were complex, requiring careful handling of toxic and reactive chemicals, but they were achievable at scale. American chemical companies were already producing the necessary compounds in large quantities, building the industrial base that would support a sustained rocket program. This infrastructure, invisible but essential, was as much a part of American superiority as the fuel formulations themselves. The Germans had never built equivalent industrial support, had always operated with resource constraints that limited what they could attempt. The testing continued through 1946 and into 1947, each mission adding data to the growing body of knowledge about hypergolic propellants and their applications. The German scientists became proficient in working with the American fuels, learned the handling procedures and safety protocols, contributed to the refinement of engine designs. But they remained conscious that they had not invented this technology, had not pioneered this path. They were learning rather than teaching, adapting rather than leading. Some evenings, small groups would gather in one of the barracks rooms, sharing cigarettes and coffee, talking about the future they could see taking shape. The conversations ranged across technical problems and philosophical questions, mixing German and English as they struggled to express complex ideas across language barriers. They discussed orbital mechanics and payload weights, but also larger questions about the purposes of spaceflight, about what humanity might achieve beyond Earth's atmosphere. The American propellant technology had made such conversations more concrete, had transformed abstract speculation into engineering planning. Wernher von Braun began giving lectures to American audiences, speaking about the future of space exploration with his characteristic enthusiasm and vision. But his presentations now incorporated the American fuel innovations, showing how hypergolic propellants would enable missions he had once thought decades away. He was adapting his dreams to American capabilities, reshaping his ambitions to fit the technology that actually existed rather than the technology he had imagined. This was pragmatism, but it was also a kind of intellectual surrender, an acknowledgement that the future he had envisioned would be built with American tools. The rocket fuel that had amazed them on arrival became routine through familiarity, but its significance did not diminish. Every time they prepared an engine test, every time they watched those chemicals meet and ignite, they were reminded of the lesson it had taught them. Superiority in one domain did not guarantee superiority in all domains. Past achievements did not ensure future dominance. The world of technology was larger and more complex than any single nation or program could encompass, and leadership required not just brilliance but also resources, infrastructure, culture, and vision. By 1948, the German scientists at Fort Bliss had become part of the American rocket program rather than a separate entity within it. Their integration was incomplete, marked by accent and background, but they were collaborators rather than captives. The fuel technology had been the visible sign of a deeper truth they had needed to learn, that they had joined a program with its own strengths and innovations, a program that would shape the future of spaceflight according to American priorities and American capabilities. The hypergolic propellants continued to evolve, new formulations tested and refined, performance characteristics optimized for specific missions. The Germans contributed to this evolution, adding their knowledge to the collective effort, but they did so as participants in an American enterprise rather than as the acknowledged masters of rocket science. The relationship had been permanently rebalanced by those first encounters with fuel technology they had not expected, could not match, and had to respect. In the desert heat and the laboratory sterility, a new generation of rockets took shape, powered by fuels that ignited on contact, that brought reliability and precision to the ancient dream of spaceflight. The German scientists who had arrived expecting to enlighten found themselves enlightened, their understanding expanded by innovations they had not imagined. It was not the outcome they had anticipated, not the role they had expected to play, but it was the reality they inhabited, and gradually they learned to value it for what it actually was rather than mourn it for what they had imagined it would be. The years passed, and the rocket program matured, and eventually the German scientists became Americans themselves, naturalized citizens working toward goals that transcended national origin. But they never forgot the fuel that had challenged everything they thought they knew, the chemical compounds that had rewritten the hierarchy of rocket science. It remained with them as memory and lesson, a reminder that knowledge was always incomplete, that assumptions were always vulnerable to reality, that humility was not weakness but wisdom. And there were thousands more such moments in history, waiting to be remembered, when certainty met reality and was forever transformed.